everybody, welcome back to Mathematical Statistics. Today we're going to talk about deriving confidence intervals from scratch. And if you don't know what those are, that's okay. We're going to do that from scratch as well. But first, I had a couple of things I needed to say that were kind of remnants of our last class. So this is just sort of some odds and ends. I didn't really have a subject matter for this. In our last class, we were trying to find the distribution of the sample variance. We ended up finding the distribution of n minus 1 times the sample variance over sigma squared. And my screen. And we, along the way, came up with an expression like this. I had something called W equals W1 plus W2. We had that W1 and W2 were independent. We had that W had a chi-squared distribution, and W2 had a chi-squared distribution, and we ended up showing that this had a chi-squared distribution. Now, W1 is W minus W2. So a question I wanted to ask you is, do you think that subtracting two chi-squareds gives you another chi-squared? The answer is no. And the easiest way to see this is not to do any transformation, but to note that the chi-squared distribution as a particular gamma distribution takes on values between 0 and infinity. So even if these were completely independent, especially if they were independent, then I could potentially get a negative number there because this could be anything from 0 to infinity, and so could this. And so if the second one is bigger, I get a negative number, and a chi-squared cannot be negative. So no, it is not true in general that a difference of chi-squareds is chi-squared. It did work out in this case, but it's really because of how it was built up. It was built up in a way that this minus this was never going to be negative in the first place. So that's the only thing I wanted to point out. It may have appeared that I said that a difference of chi-squareds is chi-squared, and that is not true in general. The other thing is I kept promising you that we would talk about degrees of freedom and what that terminology means. So last time we worked a lot with the sample variance, and we showed that if you start with a normal distribution, that this statistic here has a chi-squared distribution with n minus 1 so-called degrees of freedom. So here's where this phrase degrees of freedom comes from. In this case, we're working with the statistic, the sample variance. It is the sum as I goes from 1 to n of xi minus x bar squared over n minus 1, or maybe over n if you're using the biased version. In order to estimate this, you need to first estimate the mean. You need to compute x bar. And then you can use x bar and run through this formula. And so again, in order to estimate this, I need to first estimate x bar. Once that's done, when you have an x bar, you can actually vary your data and keep the variance the same. So as an example, suppose in this class we had 3 exams total. They were all worth the exact same amount, the same percentages. And I told you that your average on all 3 exams is 93. You could make up exam scores, but you're only free to make up or vary 2 of them. The third would be locked in because I gave you that average, which has already been, in this case, estimated. So when you're estimating something based on first estimating something else, then once that first thing is estimated, you could actually move things around and still get the same, in this case, variance, or in my example, the same average, but you're only free to vary 2 out of 3 pieces of information. In the sample variance case, n minus 1 out of n pieces of information. So that's kind of the idea behind degrees of freedom. Something has been locked in and other things are free to vary. And it's really the name of a parameter for the chi-squared distribution and the t-distribution. So I've been using the terminology, but never really talked about where that came from, and that's where that comes from. It's time. it's time to do something that looks almost like data-oriented statistics. Today, we are going to talk about how to derive confidence intervals from scratch. If you don't know what a confidence interval is, that's fine. We're going to talk about the whole concept from scratch, but I know some of you have seen it in a more data-oriented course. And so what is happening here today is, let's just talk about the parameter mu, the mean of a distribution. We have been estimating mu using a sample mean, capital X bar, which is a random variable. We could use anything, really. We could use the min minus the max, which would be negative and weird, but that is an estimator as well, as long as you haven't put any qualities that you want, like I want it to be unbiased and have small variance, and I want it to converge in probability. There's nothing behind the definition of an estimator that is special, right? It's sort of any statistic you want to choose to talk about mu, a statistic being a function of the data. But let's say we are using the quote unquote common sense estimator for the mean mu. We're using the sample mean X bar. That is a point. And when someone has data and computes the actual sample mean and they get a number, that is also a point. So there's a random point versus a numerical point. And we looked at the variance of our estimators to get an idea of how predictable they are. So here's a number line, here's your unknown mean mu. We want to estimate it with some statistic, some function of the data. We would like that statistic to be usually an unbiased estimator for that mean mu. And so the statistic is random. Once you have the data and you compute it, it's a number. The randomness comes from the sampling. If you grab a sample of size 10 and compute an average, and I grab a sample of size 10 and compute an average, and someone else does, we're going to get different values. So before the sample is taken, I don't know what that X bar is going to be, but it has a distribution that is centered around the true mean mu, and we would like to have something that is kind of tightly centered around it with small variance. So that's why we talked about variance right after talking about the property of unbiasedness. But X bar as a random variable or X bar as a number, an estimator versus an estimate, these are point estimators or point estimates. Yes, I know how to say estimator. I'm just trying to emphasize estimator. We can put the information together of the estimator and the variability to give an interval estimate. So that's what we want to do today, interval estimators or interval estimates. I don't really care about you saying that correctly, and I will never try to even correct you. But yeah, I like to distinguish between estimator and estimate. So if you are in a data-oriented course and someone wants to estimate an unknown mean of a population out there, and they've grabbed a sample and they followed a formula in a box in their Stat 101 textbook, and they give you a numerical interval like, I think that true mean is between 2.8 and 5.1. What does that mean? We talked about this a little bit last time. It means absolutely nothing about your feelings, right? And how confident you are, because how do you even quantify that? And it means really nothing about probability at that point, because the true mean is unknown to us, but it is either in that numerical interval or not. I think I said 2.7 and 5.1. I'm sorry if I forgot the actual numbers, but that's a fixed interval, and mu is a fixed unknown number, and it's in there or not. There is no probability. The probability is before someone wrote that formula in the box in the book, they did the theory that, like what we're doing in this class, to say that as an interval defined in terms of a random quantity, we can talk about the probability of correctly capturing that mean mu or not. And then once we give the formula to the Stat 101 people and they actually compute it numerically, there is no more probability. So we can estimate any one of our parameters for our distributions: a mean mu, a variance sigma squared, an alpha, a beta, a p, an a, a b, a lowercase gamma. We have all these parameters, a lambda. We can estimate them with anything we want. Some estimators are better than others, but we look at a statistic which is a function of the data. And you can call any statistic an estimator. If you're not looking for something specific, like it being an unbiased estimator with small variance or converging in probability, any statistic is an estimator. So I can say, I want to estimate the mean of this distribution by taking the maximum divided by the sample variance minus the minimum. Like it's crazy, but technically it's an estimator and it's a really bad one. But again, instead of returning just the estimator, today we want to say, and a little plus or minus. Here is an interval estimator that for us is still random, but once the numbers are in, no randomness, no probability. One of the things I think you know already, if you've been in this class, or for those of you just following the videos, one of the things I really love about mathematical statistics is that it opens us up to not being restricted by assuming normal distributions and not estimating a simple mean or a variance. What if you want to estimate the B parameter out of A and B for a beta distribution? That parameter doesn't have an easy interpretation that we could then like bring to the sample. If I want to estimate the true mean, I'm going to look at the sample mean. If I want to estimate the true variance, I'm going to look at the sample variance. But what is B for that true distribution, and how does that translate to the sample? So this course opens us up to remove assumptions of normality because that's just not always a good assumption, and to move away from confidence intervals and eventually hypothesis tests of means and variances to be able to come up with a confidence interval for the lambda for an exponential distribution. And that's what I think is one of the greatest things about studying mathematical statistics. So we are going to write the formulas that are going to be put in a box for some Stat 101 person to apply. And we get to talk again about probability. All of that said, the example I'm going to start with is normal and a mean, because it's a building block and we have easy stuff to interpret, and then we'll eventually get to more general distributions and parameters. So let's just start off with a random sample, x1, x2, out through xn, from a normal distribution with mean mu and variance sigma squared. And for this example, I'm going to assume that sigma squared is known. And I want to find, or really in our case, we're deriving the formula. Derive a 95%, I am about to define this, a 95% confidence interval for mu, the mean of the underlying distribution. Here's a number line, and here's the true mean, except we don't get to see it. We don't know where it is because it's unknown to us. We are going to come up with some interval that has random endpoints, like maybe something like x bar minus something and x bar plus something. It's going to be an interval with random endpoints. Once someone gets the data, there's no more randomness. But if you take a sample and you compute whatever formula we came up with, you might numerically end up getting something like this. And then if I took a sample and used the same formula, I might get something like this. And if someone else took a sample, they might get something like this. And so here, where there's still randomness, we can talk about the probability of correctly capturing that true mean. So that's what we want to do. We want to come up with an interval with random endpoints such that the probability that the mean is between these two things is 0.95 in this case. Let's try it for this normal example. So I do want a confidence interval for the mean mu. So I'm going to start out with, how do I know about the mean from the sample? I'm probably going to look at the sample mean, x bar. In fact, I will eventually write out confidence intervals in steps, and the first step is going to be to choose a statistic. So often it will be the common sense statistic. If you want a confidence interval for a mean, you should probably look at the sample mean, but you don't have to. And if you want a confidence interval for the variance sigma square, you should probably look at the sample variance, but you don't have to. We're going to talk about qualities of these confidence intervals and whose are better. So if you choose your own statistic and I choose one, we'll get different results. But yeah, we want to try to evaluate what's going on here. So let's just start off with Again, I'm still in this example. Let me actually copy and paste this. I am going to start by considering a sample version of this parameter. So X bar, or alternatively, considering any statistic we can work with. And that doesn't make sense right now, but after we go through some steps here, you'll see that, oh, I can't do this if I had chosen that. That sort of thing. What is the distribution of this statistic? We know that it has a normal distribution, and this is not the central limit theorem. We don't need a large sample. This is because a linear combination of normals is normal. So definitely normal here. And the mean for X bar is always the mean for the original distribution, and the variance for X bar is always the original variance over N. So once I've chosen this statistic, I want to look at its distribution and check this out. Let's define a new statistic, Z. I want to standardize this and turn it into a standard normal. So I'm going to take X bar and subtract the mean for X bar and divide by the standard deviation for X bar, which in this case would be X bar minus mu over sigma over the square root of N. Usually we just go right there. You wouldn't write this step, but I am still getting the question about sometimes you have a square root of N, sometimes you don't. When I'm standardizing normals to a standard normal, I'm always doing this exact same thing, subtracting a mean and dividing by a standard deviation. It's just that for a specific example, like a sample mean, the standard deviation has a certain form. So it's always the same, but the final statistic may not look like it because this happens to involve a square root of N. I hope that makes sense. We know that this has a normal distribution with mean 0 and variance 1, a standard normal distribution. I can find numbers that Z is within with sort of the right probability. So let's consider putting Z, a standard normal random variable, between two numbers. I'll just call it like question mark and question mark prime. And I want to choose those numbers so that I get probability 0.95. This is going to be a Z table calculation. Consider the picture of the standard normal distribution, the bell curve centered at 0 that it can never manage. That's one of my better bell curves. But centered at 0, I want to find two numbers here that capture that probability or area. And I will say something about this later, but I am going to put that right in the middle. I'm going to do something symmetric here. So like a question mark and the negative of the question mark. I do not have to make this symmetric. Again, I'll come back and talk about why I'm doing this. But let's find two numbers here that capture this area in the middle. If we're going to go to our Z table, that is a table of CDFs, of cumulative probabilities. So I need to kind of translate this first and say, look, I'm really just trying to find this question mark, and then I'll take the negative of it. So if I just consider that alone, and I have area 0.05 over 2 in each tail of the distribution, and that means I'm looking for a number that has area 0.95 plus the 0.05 over 2, which is 0.975 to the left. You may recall, you may not, because I didn't use the terminology that much, but a number that cuts off a specified area for a distribution is called a critical value. And let's go to the Z table to get this critical value here. Recall that this table has its critical values down the first column and then the final digit of it across the, as the row header here, and the probabilities are in the body of the table. So to find a critical value, a number that cuts off a certain area, we're going to have to read this table in reverse. We're going to have to look for the area we want sort of in the middle of the table. So I'm looking for 0.97, what did I say? 0.975. And that is here. If you can't find it exactly, go with the closest number. You could interpolate between the numbers, but I don't think it's worth it in any sort of increase in accuracy. So I'm just going to say go with the closest number. In this class, we won't be going with numbers at all. We're going to use a symbolic value, so we will have it exact every time. But going back to the row header and the column header, we see that is the number 1.96 for the standard normal distribution that cuts off area 0.975 to the left. So this number is 1.96. This again is a critical value. So let's go back up here. I'm going to start actually with the 0.95. 0.95 is the probability that a standard normal is between 1.96 and negative 1.96. I'm choosing to make this symmetric for a reason that I'll get to, but I could slide maybe like this line a little bit to the left and then slide the other one as well. It wouldn't slide an even amount though, because one of them would be losing area and the other one would be picking it up at a different rate. What was Z? Z was X bar minus mu over sigma over the square root of n. Let's plug that in. And remember what we're trying to do. We're trying to find an interval with random endpoints that captures mu in the middle with the desired probability. So the final step here is going to be to solve for mu in the middle. However many steps that takes you, maybe multiply across by this and subtract this, but then you have minus mu and multiply through by a negative or whatever you do. But we're going to get to X bar minus 1.96 times sigma over the square root of n less than mu less than X bar plus 1.96 sigma over the square root of n. Here are two random quantities that capture mu between them with the designated probability. So A, 95% confidence interval, I'm going to abbreviate already, for mu in this example, I'm a little too lazy to write, for the case where you're working with a normal distribution and sigma squared is known, is given by X bar minus 1.96 sigma over the square root of n to X bar plus 1.96 sigma over the square root of n. And if you've ever seen a confidence interval, you've probably seen something like this written as just X bar plus or minus. But in here in MathStat, we're not always going to have symmetric intervals, so you're going to find you often have to write out both endpoints. But we have done it. We have found A, not the, but a 95% confidence interval for mu. We could start with a different statistic, not make this based on X bar, and we could decide to not put that area in the middle under the Z curve. But let me go back to that Z curve picture, the standard normal PDF. We captured area 0.95 between 1.96 and negative 1.96. And you could pick two different numbers and you would technically still have an interval that has mu in it with the right probability. But if in this case, for this distribution, say we moved this right endpoint a little bit to the left. Because this region here is kind of towards the center where there's a lot of area, this would subtract out a lot of area from the 0.95. And so we would also have to move the left endpoint, but it wouldn't move by the same distance because there's less area out here than there is here where you're towards the center. So the left endpoint would move over further. So you would have like a number 1 and a number 2 here, and your two numbers would be further apart than negative 1.96 and positive 1.96. That's okay. It's technically still a 95% confidence interval if you chose the numbers to capture the right area, but it would be nice to give the smallest interval. Like, why would you want to say uh, a 95% confidence interval is from here to here when you can say it's from here to here and just have more precision? So I chose the area to be in the middle of the curve, and we can kind of see, I hope that makes sense to you, that that would give us the smallest confidence interval. In other problems we're going to do in here, it's not so clear how to choose the numbers. We're going to have non-symmetric distributions. So you could either do calculus to try to figure it out, um, which is going to give us like minimize the length of the interval. And in some cases, you really can't tell at all. So we can't come up with an optimal interval all the time. We'll get practice in that, but this is our first confidence interval for the normal distribution, for the mean, when the variance is known. To kind of pull this all together just a little more generally, let's get away from the 95%. So suppose we have x1 through xn, IID, normal, mu, sigma squared, and suppose that sigma squared is known. I promise you we're going to get rid of that assumption soon. If we don't want a 95% confidence interval, but a more general percentage, you might think of saying like a p% confidence interval or an alpha% confidence interval. But for historical reasons that have to do with hypothesis testing and hypothesis testing coming before confidence intervals, in the history of statistics, we usually derive we call it a 100 times 1 minus alpha percent confidence interval, or mu is given by, so I'm about to put a formula in a box, and there are many, many things I could write here. But let's just mimic what we just did in this general percentage. If we're talking 95% confidence interval, then that makes this 1 minus alpha 0.95, and that makes alpha equal to 0.05. So generalizing, if you go through the same procedure as before, you're going to end up looking at the standard normal distribution centered at 0 and trying to put area 1 minus alpha in the center. And then equally dividing, for reasons we just talked about, the remaining area alpha in both sides. So that would be alpha over 2 up here and alpha over 2 down here. I don't know if you remember this because we talked about it very briefly, but we have notation for this so-called critical value. Again, a critical value is a number that cuts off a desired area. We call this lowercase z. That's why I tried to make it a little curly. It's lowercase, it's not random. Sub alpha over 2 to be the number that cuts off area alpha over 2 to the right. This is not universal. Sometimes if you see this notation, the subscript will be the area to the left. So I am always going to have my subscript for critical values be the area to the right, and I'm going to stay consistent. But be careful, as usual, if you're using other resources to study statistics, that you are interpreting what they're doing correctly. Now, this critical value here that has area alpha over 2 to the left has area 1 minus alpha over 2 to the right. So technically you could call this lowercase z sub 1 minus alpha over 2. But by symmetry of this distribution about 0, this is just going to be the negative of z, just really trying hard to make them look not random. It's going to be the negative of z alpha over 2. So this is in place of our 1.96, and to finish the line that I started writing up here, it's given by x bar plus or minus little z sub alpha over 2 times sigma over the square root of n. There is a formula in a box that the Stat 100 people are using. But we could start with different statistics, and we could do this completely differently, and we are eventually going to not even have the normal distribution. It's going to be awesome. Let's look at another example. Suppose I have x1 out through xn IID, actually I have notation for this now, so I'll use it. Squiggly line has the distribution IID from some distribution with mean mu and variance sigma squared. So there's no n there. I'm not saying a normal distribution. And let's say that sigma squared is known. And suppose we want to derive a 100 times 1 minus alpha percent confidence interval for the unknown mean mu. Without knowing the distribution, we actually can't do this exactly. So I'm going to say derive an approximate large sample 100 times 1 minus alpha percent confidence interval for mu. Because we want an interval for mu, the true mean, we would probably start with the sample mean. And the distribution, our last example, we said this has a normal distribution with mean mu and variance sigma squared over n, and we continued. Now, we don't know the distribution, but if we have a large sample, n greater than 30 or 40, we can say we have something that's approximately normal. Putting approx over my squiggly line is informal. It's actually asymptotically normal, and we have a convergence in distribution statement. But I'm just trying to get across the point that it acts like a normal random variable when n gets large. So this is an informal thing to put over that squiggly line. And that means you can think of it as normal and do the exact same steps. So we would get the conclusion that an approximate 100 times 1 minus alpha percent confidence interval for mu when sigma squared is known, the distribution is unknown, and the sample size is large, we're going to get the exact same thing. It's approximate, but x bar plus or minus z sub alpha over 2 times sigma over the square root of n. So like this could be another formula in a box in that Stat 101 course. And this is why, because we're using the central limit theorem. So this is by the central limit theorem that gives us that normality approximately, because n is not infinite for our sample. And that's why we want to use the critical values from the normal distribution. Okay, let's look at another example. Suppose I have x1 through xn, IID from some distribution, I'm not naming it, with mean mu and variance sigma squared, and sigma squared is unknown. And I want to derive an approximate, because I don't have the name of a distribution, so I can't really work with exact quantities, an approximate 100 times 1 minus alpha percent confidence interval for the unknown mu for large samples. So, a large value of n greater than 30 or 40 or much larger. I prefer, because let's not even cut it close. So now I don't know sigma. So if I give an answer like this, it's useless. No one can use that formula because x bar is something they can compute once they get their data. But sigma is not a quantity computed from data. It's a true theoretical standard deviation. So what you might do here is say that you're going to approximate mu by x bar, and you're also going to approximate sigma squared by an estimator. Let's use the sample variance, our s squared. And we know that x bar is roughly normal mu sigma squared over n by the central limit theorem, as long as we have a large sample. And we also know that s squared, whether you use the n minus 1 or not, or use the n, converges in probability to sigma squared. So there is your justification for, if I have a large sample, I think we should be able to use s squared, the sample variance, in place of sigma squared, because we know it's approaching it in at least this one sense and in other senses. So that is often done as well. And the approximate confidence interval would be given by x bar plus or minus z sub alpha over 2. And I'm just going to replace the sigma with an s being the positive square root of s squared. So this would work as an approximate 100 times 1 minus alpha % confidence interval if you have a large sample. And again, I used the central limit theorem to get normality. But even if you started with a normal distribution, so if I started with the x1 through xn normal, if I didn't know sigma squared and was using s squared instead of sigma squared, I would need a large sample for this to work, for s squared to be a good enough estimator for sigma squared. Kind of. I have another example coming up. I don't know what number example this is. I haven't been keeping track. Here, I'm going to use a potentially small sample. So this would work for large samples as well, but you would have to do something like this if you had a small sample. So potentially small sample. If we want a confidence interval for the true mean, we need to know the distribution. We cannot say that, oh, I'm going to estimate the mean mu with x bar, and x bar is approximately normal by the central limit theorem. No, we need to know the underlying distribution because we cannot use those asymptotics to get normality from that sample mean x bar. We've seen that the sample mean for gamma random variables has a gamma distribution. So if we were working on a confidence interval for like a gamma and maybe for the beta parameter, we could work with x bar there and use the fact that it has a gamma distribution and get those cutoff values from a gamma distribution, not a z-table. And that is where we're headed. But for this example, if I have a small sample, then I definitely need a distribution. So let me make this example x1 through xn, IID, normal, mu sigma squared. I've always been saying sigma squared is unknown, but we wouldn't be doing any of this if mu was known. So mu and sigma squared unknown. I didn't change it. Mu was always unknown. And don't have a large sample. So I can't or don't really want to replace sigma squared with s squared because I don't think it's a great estimator for small samples. I do in this example have normality. So x bar as an estimator for mu does have a normal distribution. It's not by the central limit theorem because I have a potentially small sample, but it is a linear combination of normals. So we know that x bar minus mu over sigma over the square root of n is normal 0, 1. And that's kind of how we started our confidence interval. We called that z, and then we found critical values that cut off the right area for this standard normal z distribution and went on and on. But our answer involved the unknown sigma, so that is useless. And we just said that we can replace sigma with s, the sample standard deviation, if the sample size is large because it's a good estimator. But here, I can't do that. So I think that the sample variance may not be a good estimator for sigma squared if n is small. What we're about to do would actually also work for large n, but it would be what you would have to do if n was small. Because if you had a large n, you could probably return this confidence interval and use those large sample properties for x bar and s squared. Again, small sample, you must have a distribution. And after this example, we're going to start to get into the other distributions and see the exciting math stat stuff. But one more normal distribution, and I want a confidence interval for the unknown mean mu. And yes, we will eventually get to confidence intervals for the unknown sigma squared. So I do know that this is true, but it's not useful. The question is, if you did replace the sigma by a capital S, how is this distributed? It's not normal 0, 1 anymore, or not approximately normal 0, 1 because of the potentially small sample. So we're going to figure out the distribution of this quantity right now. This is a rather large aside for the example, so yeah, let me clearly mark this. I'm about to go off the rails. If we have x1 through xn, IID normal, mu sigma squared, I want to know the distribution of x bar minus mu over s over the square root of n. We already know x bar has this normal distribution. So check this out. I can write this as x bar minus mu over sigma over the square root of n. Now that's not equal to the line before, so I'm going to need to compensate by multiplying by a sigma and dividing by an s. That is in fact equal to the line before, and we know the distribution of this is normal 0, 1. What is the distribution of this times this? This is complicated because s is a random variable. So it's not just like I'm multiplying a normal by a constant, I get another normal. Let's do a little rewriting. What if I wrote this as x bar minus mu over sigma over the square root of n, and I put s over sigma flipped over but in the denominator? Better yet, what if I put s squared over sigma squared under a square root? Better yet, if I put an n minus 1 in there, I'll get something I know the distribution for, starting with a normal distribution. So let's write this as x bar minus mu over the square root of n minus 1 s squared over sigma squared, all over n minus 1. That's all under a big square root. Oops, I forgot part of my numerator missing. This is x bar minus mu over sigma over the square root of n. Check this out. This has a normal 0, 1 distribution. And starting with normals, which is our assumption here, this quantity in here has a chi-squared n minus 1 distribution. And you saw on homework problem number 6, and we did this pretty much in the last class, that for a normal distribution, x bar, the sample mean, and capital S squared, the sample variance, are independent. And that means these two quantities I've circled are independent. So are you seeing what I'm seeing? I see a standard normal divided by the square root of an independent chi-squared divided by its degrees of freedom. That's how we define the t distribution. This whole thing has a t distribution with n minus 1 degrees of freedom. So to go back to the actual confidence interval, I can't start with this because we don't know sigma, but we can start with this and look to the t distribution for those critical values for the right cutoffs. So let's do it. Just to be clear, let's say back to the example. I have x1 through xn, IID normal, mu sigma squared, mu and sigma squared are unknown. I want a 100 times 1 minus alpha % confidence interval for mu, and I can't assume a large sample. So I'm going to start off with an estimator for mu, or a statistic, x bar. And, I said at the beginning, you could use anything you want as long as you can work with it. We had additional steps. We needed to find a function of this statistic and the thing we're trying to estimate whose distribution is known to us and unknown parameter free. And if you pick just any statistic here, you may not be able to do the next steps. So you can't just choose the common sense estimator for the thing you want the confidence interval for. You also have to choose something for which you can pull off the next steps. We're going to get a lot of practice, so you will see. But X bar has a normal distribution because we're starting normal with mean mu and variance sigma squared over n. And we're going to start with X bar minus mu over S over the square root of n. You know what? Let me back up. I'm sorry about this. This is right, but I want to write out the steps. I haven't really delineated steps so far. So step 1 is going to be to choose a statistic to work with to make your confidence interval. At this point in the course, I'm going to give you one. On your homework, I'm going to say, find a confidence interval based on the maximum. I'm going to give you this. But let's look at X bar here. So again, in your homework and exams, I'm going to give you the statistic you should use and then eventually not, because we'll have ways of figuring out the best statistic to use. But this is what I would call step 1. Step 2 is going to be to find a function of the statistic and the unknown parameter whose distribution is known, and this is kind of maybe making it sound more complicated, unknown parameter free. What the heck does that mean? In our example where we knew S squared, we wanted a confidence interval for mu. We considered the statistic X bar, and we turned it into something standardized. And this was known, so we could go to that distribution and get critical values, get cutoffs. But if this distribution depended on mu, I would not be able to find the cutoffs because mu is not known. So we want a distribution. We want to take our statistic, our estimator of this, and find a function of it and the thing we're trying to estimate whose distribution we can work with. This is going to inform your step 1 going forward. You can't just choose anything. You can't always choose the common sense estimator. If you find you can't do step 2, you have to back up and choose a new statistic. Okay, so in our example, we actually don't know sigma squared. So I am going to, yeah, maybe the wording isn't so good here. I am going to use the function x bar minus mu over S, capital S, over the square root of n. This function of the statistic and the unknown parameter whose distribution is completely known to you is called a pivotal quantity. So if you see pivotal quantity in a stats book, that's what they're talking about, a statistic that has been adjusted by an unknown parameter in a way to give you a distribution that is completely known to you. In the past, we've had, pivotal quantities look like this, but right now I'm going to use this one because I don't know sigma. And yeah, the distribution, what is it? It is, we just showed for this example, a t distribution with n minus 1 degrees of freedom. So step one was to choose a statistic. Step two was to find a pivotal quantity, which is some function of the statistic and the parameter you're trying to get at, whose distribution is known to you and does not depend on any unknown parameters, because that would make it kind of worthless. We are assuming we do know the sample size, so n is known to us. Okay, so I'm calling the next thing step three. Like if you might in your mind combine two of these steps and just say, I think the whole process has only 3 steps, not 4 steps. That's okay. But step three is going to be, in my book, to find critical values, let's say appropriate critical values, based on the distribution you just named above. Again, t-distribution here, it is a bell curve centered at 0. So this is supposed to be the PDF for the t n-1 distribution. This is a horrible PDF and it is not integrable. After this, we're going to work with PDFs where we can actually integrate and find critical values using integrals and not tables. But for the t-distribution, there is a t-table. So did I give the instructions? Yes, 100 times 1 minus alpha percent. So let's put area 1 minus alpha in the middle, alpha over 2 on each side for reasons we talked about. You could slide this around. And then these two are critical values. And because this is symmetric about 0, I really just have to find one of them and the other will be the negative. And then the notation I'm going to use is similar notation. It's going to be a little t sub alpha over 2 to be the number that cuts off area alpha over 2 to the right. So this is a critical value, but that alone does not describe the distribution. So included in this subscript, I'm going to put comma n-1. You might see t sub alpha over 2 of n-1. That's okay too. I don't care what you use on your homework or exams. If you want to call this number A and this number B, as long as you say where B is the number that does this, that's okay too. As long as you've defined your symbols, I don't care what you use. Okay, a T table. For our generic confidence interval, the answer is going to be in terms of this. Let's finish this one off and then just check out a t-table. Okay, step 4. Put the pivotal quantity from step 2 between the critical values and solve for the unknown parameter, quote unquote, in the middle. Okay, in our case, we get area 1 minus alpha if we put like a t random variable where t is a t distribution with n-1 degrees of freedom. One of several ways we can do this is to put it between the critical value t sub alpha over 2 comma n-1 in our new notation. And because this distribution is symmetric, negative t alpha over 2 n-1. And then let me plug in what our statistic is. It was x bar minus mu over s over the square root of n. And then you want to solve down and get mu in the middle. And then the side things are going to be the endpoints of your confidence interval. So the answer here, and it's not a unique answer, is if we have a normal distribution. We don't know the mean, we don't know the variance. We want an exact confidence interval for the mean, but again, we don't know the variance. We don't have a large sample, so we can't do an approximate confidence interval, but we don't know sigma squared. If we start out with S, instead of sigma squared, we're working with a t-distribution, and the answer is going to be x bar plus or minus t sub alpha over 2 comma n-1 times capital S over the square root of n. I actually didn't use anything having to do with small samples in this example. If you have a normal distribution and you want a confidence interval for the mean mu and you don't know sigma, so you use capital S, it's a t-distribution that you should be looking at. However, people often don't bother if they have larger samples. The t-critical values get really close to the z-critical values. So again, the thing I just put in a box is a formula that doesn't depend on the sample size being small. You could even use it for a large sample size. Let's check out a critical value, an actual critical value. So maybe we want like a 95% confidence interval. Then we would want t sub 0.05 over 2 n minus 1. Let me do an example. So let's say n is 10. So I would want 10 minus 1. In other words, I'd want t sub 0.025 comma 9. This is supposed to be for a T9 PDF, two numbers that give us area 0.95 in the middle. And then this number here is T 0.025 comma 9, which is really a number that gives us area 0.975 over here. I've got a t-table for you. You can find one on the Canvas page. If you don't have access to the Canvas page and you're watching this video, t-tables are everywhere, or you could use software, but it doesn't really matter for this course because we're going to be sticking to things that look all generic like this. But here is a t-table. Now, most t-tables look different from z-tables because of that degrees of freedom parameter. We could be looking at a T1 distribution, a T2 distribution, a T3 distribution, and we could have a z-table type thing for every one of those distributions, but no one carries that stuff around. So typically you'll see a table like this. This particular table is using my notation. T sub alpha captures alpha area to the right, although it's not showing the degrees of freedom. And how do you read this table? The column here is the degrees of freedom parameter. So we want n minus 1 or 10 minus 1. We want 9 degrees of freedom. And then unlike the z-table, a t-table usually has the critical values in the body of the table and the probabilities up top. So we're actually very limited here in the probabilities that we can cut off, at least using a t-table. You can go to software to find this. So this particular table, it might be different depending on what you're looking at. T sub alpha captures alpha area to the right. We want area 0.025 to the right, so that's right here. And we want it for 9 degrees of freedom, so it looks like we want this number, 2.262. And yeah, that's it. So we are ready. Again, I'm not spending a lot of time on this because we're not doing really much numerical stuff, but 2.262 for the T9 distribution. Cool. Let's move to a different distribution. Get away from normality. Let's see if we can apply the techniques we've learned here to a general parameter, or not general, but to a different kind of parameter, not a mean, and a different distribution, not a normal. So here is, looks like probably our last example for today. Suppose we have x1 through xn, a random sample, or equivalently IID, from the exponential distribution with rate lambda. And let's find a 100 times 1 minus alpha percent confidence interval for lambda. So this is really the most important part, I think, of today. Can we apply this generally? Based on the minimum in the sample. I don't think this is a good idea, but it's something we can work with. And we're going to do other confidence intervals for lambda for the exponential and compare this. So again, we are at the point in the course where I'm going to give you based on. I'm going to give you step 1. So let's try it. Just for completeness, I'm going to write step 1, which is going to be to choose a statistic You might say choose an estimator, but even though an estimator does not mean anything specific, that does make me think that it should make sense. Like why would you estimate lambda with the minimum? You certainly can, so you can call it an estimator, but let's just call it a statistic. So this is done. At this point in the course, this is always going to be done for you. All right. Step 2 is to find a pivotal quantity. Recall that this is going to be some function of the statistic and the unknown parameter, in this case lambda, whose distribution is known to us and not depending on any unknown parameters. Not only do we have to name the distribution, but it can't involve lambda. We can't say the distribution is this with a lambda in it because that's not useful. So once you've chosen a statistic, for finding a pivotal quantity, the first thing I would do within step 2 is look at the distribution of the statistic. You may recall from much earlier on, from the first weeks of this course, when we learned about minimums and maximums, that, oh yeah, I should be clear in case you forgot this notation. This is the minimum of x1 through xn. So we did show that the minimum of n IID exponentials with rate n lambda is again exponential with rate n lambda. If we didn't know this, then at this point, we would be applying our beginning of the semester skills. We would go off and try to find the distribution of this. This one happens to be one we've already seen, so you may or may not remember it, but I'm just going to write it down. But yeah, at the beginning of the course, I gave you several statistics and said, find the distribution. So you might have to do this part from scratch. Okay, I want to find a function of the minimum and lambda whose distribution is known to me. Checking the time. What? My clock stopped. Yikes. I want to find a function. I think I have a couple more minutes. So I want to combine the minimum and the lambda into something whose distribution is known. And don't think of, you know what, I'm not going to be able to finish this example, but let me just tell you what not to do. So the mean for the minimum is 1 over its parameter, and the variance for an exponential is 1 over its parameter squared. But this is not useful. You're not going to want to look at x1 minus its mean. Finding a pivotal quantity does not mean standardizing the variable. That's just what we do for normal distributions to get to a normal distribution we can work with. We want to find any sort of function of the minimum and lambda whose distribution is known to us. So I'm going to leave you with this thought, and we'll finish this next time. To make the notation a little bit easier, suppose you have x exponential with rate lambda. Consider finding the distribution of a new random variable y to be a constant times x for a constant c greater than 0. So why don't you check that out before we come back? You're going to find a nice known name distribution, and you're going to see the parameters have mixed up c's and lambdas, and maybe we can choose c appropriately so that we have a pivotal quantity, something whose distribution doesn't depend on lambda. So we will pick up with the begin. I'll start this example over next time. You know you're coming back for this. This is where it really gets good. So I will see you next time on mathematical statistics.